Good afternoon and welcome to the first seminar in our GSQ Geoscience Data Seminar Series. My name is Mark Gordon and I'm the Director of Geoscience Information within the Geological Survey of Queensland. Firstly, just a little bit of housekeeping. In my role as MC today, I'm going to provide a quick overview and introduction to today's session, and then I'd like to hand over to Steve Bowden, who is our Principal Data Manager, and Steve will present for around 35 minutes. During Steve's presentation, if you have any questions, please feel free to put them in the Q&A function, and we'll try to answer as many of these as we can at the end of Steve's presentation. We'll also be sending a very short survey to you at the conclusion of the session. So if you could please take a moment to complete it, it'd really be very much appreciated because it helps us understand what you would like to get out from these particular sessions. Today's presentation by Steve is the first in a four-part series we're establishing to provide industry with some insight into the data and digital work we're engaged at within GSQ. I can assure you there's a lot going on in this space, but it tends to happen in the background and it's not socialised in forums such as this, as much as perhaps other geoscience-related topics are. This particular seminar series is about putting that right and sharing some of this activity, most particularly how the work that we do here in Geoscience Information might directly benefit explorers. The GSQ began the journey to modernise our data systems in 2019, and we had a primary goal of publishing all the open data we hold into a system which made search and discovery of the data simple and easy for all to use. With that in mind, we completely realigned our approach as to how data was structured at the back end of our systems. And this was through adopting new models and approaches that better supported how we wanted this data to be represented. This ensured that whatever we put in place would be really robust and extensible and would stand the test of time. Certainly our work on knowledge graphs and vocabulary as part of the topic on the table today have really underpinned a great part of our implementation so far. And with that, I'd like to now hand over to Steve. Steve has extensive experience in both knowledge graph and vocabulary domains and is going to share with us some of the work we're doing in this area right now, as well as where we plan to take it over the coming months and years. Thanks, Steve. Over to you.
All right, yeah, thanks Mark for the introduction. So yeah, today we'll be talking about geological things, semantic modelling at the Geological Survey of Queensland. So first off, I'd just like to do an acknowledgement of country. I'd like to acknowledge the traditional owners of the land on which we meet today. I'd also like to pay my respects to elders past, present and emerging. So just a bit of background. Mark's covered a fair bit of that as well. But just, the Geological Survey is the state's custodian of geoscience knowledge and data. In 2018, GSQ celebrated its 150th birthday. The state's first geologists, Richard Daintree and Christopher Applin, were appointed in 1868. So over that time, storage and retrieval of data, we've been collecting observations all this time. So storage and retrieval has evolved from paper-based. It's moved to things like local servers. And then moving now, as Mark explained earlier, moved into the cloud and providing data through access through the internet on geoscience.data.qd.gov.au. So what are the next steps? We want to get into the space of data interoperability, so we can communicate data to and fro, and also representing more meaning out of the data that we're producing. And that I'll unpack that a little bit more in this presentation. So why are we going down this path? Why we stopped at just serving off the data? Well, new mineral discoveries have tapered off. Most of Queensland is covered by young sedimentary rocks, and it's the brownfields that are already being mined and worked on are fairly well understood. We've got critical minerals in play now, so we're looking for lesser known critical minerals, which aren't necessarily the targets of old reporting, so it's hard to pull them up and find particular reports about these things. And so as a result, a bit of innovation is required to get to that information that's stored in that large repository of data. So we're going to put data is at the center of discovery, and it's becoming more and more evident that's the case. And nowadays we have the cloud, the computing power of the cloud, plus AI tools and techniques at our hands and fingers and hands. So we can actually make use of this stuff now. And so it's good to start looking at our foundational data and making it complete, consistent, interoperable, and meaningful. But we're not alone. This is not a new problem for us. A lot of organizations have had the same situation. And back in 2006, we had the Linked Open Data Initiative, which sort of kicked off by Tim Berners-Lee, who was the inventor of the World Wide Web. And he sort of classified data into these 5 categories, 5 steps of maturity, for example. So you have your 1-star data, your 2-star data, up to 5-star data. Your 1-star data is about making it available, get it online. And a lot of companies are already doing this with blog sites and whatnot. The second step is make it readable. So putting up data in structured format like a spreadsheet. And we're doing that a lot with open data, and you can download spreadsheets, and even with CSV files, that's the next level up. That's getting away from the proprietary formats, so make it non-proprietary, and using serving up data in that sort of format. Then we move into the next level, which is the RDF format, which is not just make your data available and non-proprietary, but give it a web URL. And it's a bit of a strange concept, but the internet works, right? And we've been able to connect with things on specific locations, particular servers all over the world using web URIs. So why not attach web URIs to our data? So that's where RDF comes into play. And then once you've done that, that 5-star data level is where you're linking it together, and you've got you've got data which has web URIs that you can bring in from other caches of data that also has web URIs. But getting to this point doesn't mature organically. The challenge is, like most websites and applications, run perfectly well on 1-star data. In fact, it's probably counterintuitive for a website to put their data into that 2-star level, because somebody could just scrape, for example, recipes. If you had a recipes website and a blog about recipes, someone could scrape that Excel file off their website and make their own little recipes website using your data. So it's not necessarily going to grow on its own. So the drivers in this space are government, academic institutions, and large nonprofits, because these areas have different agendas in mind. They're not trying to catch customers and bring them onto their websites. They're trying to progress, whether it's an agenda of government, or if it's trying to work together with other academic institutions across countries, or if you've got some sort of non-profit agenda in terms of global health or those sort of things. And also you've got, in terms of the tooling around getting this data into this space, you've got the big corporations of social media. So you've got your Facebook, your Google, and your Microsoft. And they've contributed some good products in terms of how you manage this data, given they have a huge amount of customer data that they manage, and they can get value out of that. So they've built these products, and they've socialized a lot of those with the public. So why are we moving in this direction as GSQ? It's not just because Tim Berners-Lee says it this way. We're the custodian of huge amounts of geoscience data. So we're in that space. We've got a lot of data, and we can work with it. We deliver our value through our data. So better data means greater value. And also, by harmonizing our information, the way we organize our data across jurisdictions, there's a national benefit there, because geology doesn't stop at state lines. And also the companies that are operating in the mining industry are also operating across state lines. So having some cross-jurisdictional harmonization is a benefit there. And also gives us a new way to slice and dice our data, and improving the consistency of our geoscience products. So when we have a report or some sort of product that's going out, we're talking off the same songbook. Structured and meaningful data can also propel data science. So looking at geoscience data as a whole, you've got lots of different repositories of information. You've got your downhole logs, you've got your administrative boundaries, solid geology, geophysics data, lab results, a whole bunch of stuff. And if someone was to go in there, you've got separate systems and often stored in different formats. So if someone was to go in there and want to search a particular topic or a formation, you have to cover off all of these sort of different areas and start building up and collating and building up this repository of your own research data just to find information about the same subject matter. That's why it's quite annoying. And then you've got and this information that we're trying to research from all the different systems is also coming from the same state. So geospatially, we're looking for data in the same area on the same topic, and it's all centrally collected. Oh, not all of it. We don't have all the data, but we have quite a lot of the data is coming through reporting and the historical records that we keep. So the data's here. It's about Queensland, and it's about a lot of the different systems are covering the same topics. So we want to get to a point where, the data is relatable, connected, interoperable between systems, and available for use. So people can come in directly and get into that data. So to get to that point, we have to form connections, we have to break through silos across systems, and we have to establish sources of truth within that. So how do we go about that? Through the semantic modeling of our things. So I'll have to unpack this a little bit, but this is the general gist. So what is semantic modeling? Semantics relates to the meaning in data. So that's the first part of that word. And data modeling describes data and its relationships. So when you combine the two, semantic modeling is about describing data in terms of its meaning and relationships. So it's effectively describing reality. And what are things? Things it's a very generic topic. So start simple. What is a thing? A house is a thing. An address is a thing. A cat is a thing. A pet name is a thing. And to be inside of somewhere is also a thing. And these are kind of what you call generic things. They don't deal with a specific thing in particular. So these are what we call a type of class. And on the right-hand side, we've got things that are specific. So your house is also a thing. Your address, your specific address where you live is a thing. Your cat is a thing. And your cat's specific name, for example, Puddles, is a thing. So how do we describe these things? Simple. We just use natural language, essentially. It's just how it is in reality. So we set out rules and descriptions of these things. So we create some statements like a cat can be inside of a house. A house can't be inside of a cat. So you set out these sort of statements, and you're going to say, oh, a cat can have a pet name. Or you say a house can have an address. So these are attributes that are related to those particular things. So a semantic model, so we have a statement of reality at the bottom here. Cats can have pet names and be inside houses that have an address. So how do we describe this in a model? We have our pet names, cats can be inside houses and have an address. So in general sense, that model, that picture above describes that statement below. So how do we represent data in this way? So we're looking at class before in a generic model of the broader things involved. So looking at specifically, your cat is inside your house. So here is your cat, it's inside your house there. And if we want to add extra data to that, your cat Puddles is inside your house at 42 Example Avenue. And you see how it fits the model that we had before. So by combining it with our semantic model, it gives more characteristics so we can get better information and meaning out of this here. Like it makes a bit of sense as it is, but by adding these extra features here, we can say, all right, your cat, that is actually a type of cat. It's not some other creature from another movie. And you've got Puddles, which is a name, okay, and then house, it looks like a house, but it might not look like a house. So having that surety that we're looking at houses, and 42 Example Avenue is in fact an address. So having those extra characteristics around the model helps us understand it more. So how do we decipher connected data? So what's the point of having all this description in reality? Here's a situation. You might only have to work with two bits of data. So you have, if someone was to say Puddles is inside, there's not much to work with, right? So we could query the network by having these two bits of information. Since we have a network established, we can lay those in there and establish that, all right, Puddles inside means Puddles is inside your house at 42 Example Avenue, and Puddles is your cat. And yeah, it's a type of cat. So this is all. So from a small amount of information with a model that describes the reality that information sits in, we can actually get a lot more meaning and certainty about what we're dealing with. And I know it's a geoscience talk, but from an internet marketing perspective, these types of tools are heavily used, because when you're applying the keyword model to something like Puddles is inside and you're generating advertisements for people on your website, you might put up cleaning gear because it makes sense. Puddles inside, all right, let's advertise cleaning gear because we're using a keyword model. But by applying a semantic model to that information, you're more likely to put up cat food deals in the local area. So you get more value out of what is there in front of you because you have the model behind it. So, and obviously there's applications in the geoscience space as a result of this. So going into the geoscience world, trying to apply this sort of stuff, it's obviously going to get a little bit more complex because you've got a complex, scientific field. We're not just talking about cats and houses. So it's going to get a little bit more challenging to follow, but essentially the same sort of concepts are there. So if you went at the last webinar, you might not know too much about the toolbuck, but it was discussed at the last GSQ webinar. So in isolation, the toolbuck itself is not going to mean much, but you add a little bit of context to it, not too much, just a little bit. Something like toolbuck is Cretaceous, it occupies this geospatial space, and it's a formation. So with a bit of geological knowledge, you can understand, all right, I know what Cretaceous is, that's a geological time. I know that part of Queensland and it's a formation. So I've got a bit more idea of what the toolbuck is. I was like, all right, well, since it's the Cretaceous and it's in that area, there's also the Eromanga, which is Cretaceous to Jurassic in a similar sort of area, and there's a sedimentary basin. So we're starting to establish more meaning around this data just by connecting the dots. And with a bit more knowledge, we know that the Eromanga and toolbuck are both sedimentary, and one can form some sort of conclusion, or with some site observations, we can say that toolbuck is inside the Eromanga, given they share this geospatial location, and they're also of the same time. So that's all well and good, and you can get quite a lot out of that. But essentially, when dealing with geology or any sort of complicated field, it's going to get a little bit more expansive. There's a lot more formations and features and different scales out there to work with. So as things get a bit more challenging, you'll need to apply things like controlled vocabularies. So what we have up the top there is a geological timescale. So all of these little things like Mesozoic and Cretaceous, Jurassic, Triassic, they belong to a vocabulary of timescales. And the word formation belongs to a controlled vocabulary called geofeature type. So that covers that off. And then sedimentary is a lithotype and so on and so forth. It's not, these aren't the specific ones we're using. They may be, but just for brevity and to get the point across, I've just sort of covered them off as simple as possible. And even in the way in which describe the things specifically, like the toolbuck and the Eromanga and the geospatial factors around them, they're covered in what's is called geofeatures, and we have some rules about how they are also collected and stored and recorded. So modeling, I'm summarizing semantic modeling. It helps computer systems interpret what human-generated data means. So all of that stuff, there's a method to the madness. We're not just trying to describe reality for the sake of it. Once you get systems into this format and this structure, you can actually run them through computer systems that have reasoning engines and offer powerful benefits. So it helps computer systems interpret what human-generated data means. Further, it enables an efficient interface with other computer systems. And that's come straight out of the textbook. So just to cover that off, we've got a textbook definition there. I'm just going to get through this part fairly quickly because I'm not expecting everyone to remember. But overall, there's some technical elements, and this is a bit of a reference you can come back to around semantic modeling. It starts off with XML, and then underneath that, you have this system called RDF and RDFS, which are sort of XML type of information, which can be represented in various ways on the right-hand side through the format like total, which is a simple way of looking at RDFS and RDF, and also JSON LD, which is the kind that you probably implement into an application. The data itself is stored in this RDF format as triples, and we search through the data using SparkQL. There's also, web ontology language called OWL. That's the acronym's kind of back to front. That's one of those things. And what that does, that gives the ability to create rich reusable domain descriptions for things called ontologies using this RDFS structure, which is a schema for just creating your own little ontologies. It gets a little bit complicated here, but essentially what we're working towards is getting these things called controlled vocabularies in place and other types of like the geofeatures ontologies working. The controlled vocabularies are written in this thing called SKOS, the Simple Knowledge Organization System. And then by writing things in SKOS, it's a standard system for describing knowledge. So things can have a hierarchy, things can be broader and narrower. So you can have sedimentary as, for example, as a rock, then have a narrower categories of, sandstone, siltstone, mudstone. for example, in your lithotype vocabulary, and things like that. And you can also characterize how they relate to each other. So you can say, oh, sedimentary is related to metamorphic because they're part of a a rock cycle or something like that. So there's ways, SKOS gives you an opportunity to describe your knowledge and information in that way. But I just want to cover off some of the important features here. So the triple, which is effectively you have this question: how is this data being stored and moved around? So it's stored as a triple, and the RDF triple is a way of describing the world, and it's stacked up 3 columns, fairly simple: a subject, predicate, and an object. So for example, from before we had your cat is inside your house, and your cat is the subject, the predicate is being inside, and your house is the object. So by breaking up the data into those subject, predicate, object, you can pretty much connect anything. And unfortunately, we can't store it like that. In reality, it's all done using web URLs. So that's where you would store it like this: https example.com / your cat is inside your house. And that's sort of how it lives in the system. And that's why we have those languages like Turtle and JSON-LD to help simplify the look and usability of the data. So you have repeated words, you can use namespaces and parameterize a lot of these repeated parts of text in the RDF. And that's pretty much an RDF triple. And that's sort of your data source that you'd be connecting to if you had a large description of reality. The other part I want to talk about is these controlled vocabularies, which I've sort of got to before. And I've got a little example of one here. This is a website called issemantic.net, which has an RDF visualizer built into it. And we've got one of our vocabularies, which is our seismic dimensionality vocabulary. And the purple boxes, they are the actual identifiers for the specific terms in the vocabulary. And let's see how they got that web URL. And off to the side, you've got things like the preferred label, which is a SKOS description, and that tells us what it should be called. So our preferred label is 3D seismic, but you can also call it 3D seismic survey. And it has a definition as well, the fundamental data set of a 3D seismic survey or something like that. These things also have the ability to bring in some of your standard metadata terms. If you're into metadata and all that stuff, you've got the DC terms here, you've got provenance and extra things that can sit around it, and also describes how it gets its own structure from. So it's also referencing some of the concepts, the ontologies, and the concept schemes. So that's pretty interesting to see how these are structured. And some of our vocabularies are quite complicated. This is one of our smaller ones, and it shows how you can relate them, and you can say how this one is a top concept of this one, so that's how they're connected together. And where do you store this stuff? Obviously, you're thinking in your head, all right, we've got thousands and millions of rows of information. How is it actually going to be stored? There's a thing called a triple store, and these are databases that store triples at scale. They require specialized software infrastructure to run them, but essentially, it's out there. There are systems that can do that. And with today's cloud computing power, it's not out of reach to run these types of triple stores over large sets of data. So that covers all of the technical side, but let's talk about where we're up to GSQ in terms of our journey. In 2020, as part of the Geoscience Data Modernization Project, we set our production data model around this thing called SOSA, which is a type of Internet of Things sensor-based data model. It's a generic, I think it's like an ontology which describes how everything connects together, and it's based around sites, survey, sample, observations, and results, and how they all are connected. And then ultimately, we're trying to bring it all back to a geological administrative feature of interest, and then we can assign also properties that come out of those results back to that feature of interest. So that's our general data model. It's a nice it's worth having a bit of a look at and just getting your head around. And then we've built our underlying database around that. And when you're looking at the data itself, you can go into it, and this is just using a thing called React Force Graph library. So I've gone into our geoproperties database, and it's been structured that way. You can sort of see how we've got our reports, our permits, our boreholes, and sites all sort of connected. And what we want to do is get this kind of thing connected through geofeatures at scale and center some of these kind of visualizations and explorations around things like faults and other features. So yeah, we're also using, as I said before, we're using SKOS for our vocabularies. We've got over 70 files there. They're all hosted on vocabs.gsq.digital. You can look at them here. We're getting a bit of an upgrade to the UI of this site, but underlying the vocabs are still going to remain the same. They'll be doing some also improvements on the vocabularies at the moment, but ultimately that's where you go to find them. We're also integrating vocabularies in our lodgement form. So when you're submitting data from industry, you will you'll be able to look up these vocabularies, and so when we'll be able to connect the data that's being lodged in and have it already fitting into our data models. We're also publishing our first RDF data set based on geological features. So that's something we're working on at the moment, which is, it's new because at the moment we've been mainly doing the vocabularies, the dictionaries, the terms, how they all relate to each other. But the Queensland Geological Features data set is that next step where we're actually talking about instance data, specific things. So before, with that example, we had cats and houses and things like that. But now we're talking about specific, your cat, your house, and this is specific rocks of specific formations versus rock, what type of rock, for example. So this is where we're heading in terms of getting a features data set up and running. It's a slow process, and we're sort of getting it moving first, just in terms of the general system architecture and infrastructure, and doing some tests on that. We're also getting our supermodel described on GitHub. You'll find a repo there, public repo there, which will talk about our overarching supermodel. So how we structure our data and knowledge infrastructure, the types of ontologies that we're bringing in into the picture. So that's an interesting one, and that's a lot of information there about how it all ties together. And behind the scenes, we've got validation tools and automatic deployments. A lot of the work that goes into doing this stuff is quite laborious, and it's prone to a lot of human error. So we can, by running validation tools, helps us ensure that we can have a good workflow and then load those things into wherever the production systems that are using them efficiently. On top of that, we're talking to other geological surveys across, throughout Australia about, getting our vocabularies in line, or having understanding of what each other's doing, so we're staying on the same sort of path. So where are we heading? This is just another a view of some of our data. Obviously, it would be nice to have that connected through GeoFeatures going forward. What you're seeing there is pretty much just your report or your permit that spans out into a borehole, which then has survey and results, observations coming off them. So where are we heading? We want to realize the value from linked data through our GeoFeatures dataset. So we want to start linking things up. We want to expand and improve our vocabularies, but at the moment we're focusing on geochemistry. We want to host data sets in RDF for interoperability, and we also want to test out Triple Store infrastructure. So we're going through a process of that at the moment. Also inheriting vocabularies from other authoritative sources to reduce rework. So this is an area where we can look at our vocabs and we can optimize them. So for example, geological time may be well described through another standard source. So why are we maintaining a geological time scale vocabulary when someone else, a more authoritative source has done that? And using semantic models to enhance information extraction from documents subsequent to OCR. So this is really an emerging area where we can apply this type of modeling over the reports and the subjects of those reports that are coming into us. And we can get meaning off that data, then plug them into something like machine learning to maximize the effectiveness of what we get out of the content within our reports. And also standardizing vocabulary across jurisdictions where possible. So there's a lot of discussions in that space as well. So why it matters to you. So why is it important? Obviously, semantic modeling helps us describe reality, and being geoscience, it's a highly descriptive discipline. A lot of observations are made, a lot of things are looked at and touched and recorded. So being in that, geoscience by nature really benefits from this type of modeling. Also, these days it's popular just to throw AI at problems, which is fine. AI is a very powerful tool, but to get started with that and to get the best out of it, you really want to have good structured data that's well described. And so all your training data is working off similar vocabularies and can pull extra information and dimensions and features from our semantic models. So yeah, AI demands good structure in order to be effective, and this kind of platform helps us get there. You also might unlock new insights through previously unexplored relationships. So in the social media space, it's pretty common to look at people's social graphs as a way of matching other consumers. And by then you can sort of promote advertisements or recommendations engines and things like that can stem from this sort of profile matching, and it might be able to tap into some of those cool tools in the world of geoscience as well, where we can have we have a well-known area which has a certain profile, a semantic profile, and then we have bits and pieces of a profile somewhere else, and it might just help fill in some gaps for us. It might give us deeper understanding of geological systems by using terms that we all understand, and less not having disagreements and arguments over the semantics of things when we're just trying to understand the system itself. And that's another part, is reducing that confusion and improving efficiency when we're importing and exporting data. On top of that, if you're building your own sort of system, being able to take generic data models like SOSA, it can simplify a lot of the decision making when it comes to designing your data model. If your area of interest or industry has a similar structure to what's already out there in these generic data models, you can adapt that as much as you can, and then tailor it a little bit to your specific industry, which is what we've done with geological properties, or the GeoProps system. And that's pretty much it for me. So I'm up to the questions part. So if anyone has any questions, or I can I'll just switch over to the group.
Yeah, many thanks for that, Steve. We don't have any questions in the chat, but if people have questions, I'd encourage you to pop those in now. There's a little bit, I've got a bit of an advertorial that I wanted to share with people, so I might go through that first, and we'll see if there's any questions that appeared, and we'll deal with them then. So just a couple of things I wanted to touch on. The first is that we'll be sending out an email shortly asking for registrations for our next webinar. And as I mentioned earlier, we'll also be sending out a short survey following today's session, which will really help guide us in terms of what you'd like to see in these upcoming presentations, which is, I think, why it's really important if you can get on and give us some feedback about what is it that you'd like to see related to geoscience data and or any of our systems. We'd really appreciate the guidance, and obviously we'll then be able to make it relevant for you. There is also another project and potentially another engagement that I just wanted to touch on here. Many of you may be aware through some recent communication that we're currently engaged in development of a modular reporting system, which will leverage our current lodgement portal architecture. This system will revolutionise the way that industry reporting is undertaken, and really in a nutshell, it will enable industry reports to be submitted as components rather than one large PDF. This will promote content reuse and where appropriate, and will improve data quality and make report submission more efficient through sort of being able to use collaborative tools and the application of standard vocabularies and response terms. And we've heard why they're so important just now. So as part of that system development, we're looking for nominations to participate on commodity-based reference groups, and this is to provide feedback into those systems, as well as be involved in a program to pilot the capability. If you'd like to be involved, please don't hesitate to get in touch, because the numbers within these groups are limited. We don't want to limit them too much, but we've got a cap on it. If you're looking for more information about our modular reporting system project, please don't hesitate to get in touch. Okay, that's me for my me in terms of the advertorial. I don't see that there's any other questions in the chat. So I just wanted to sort of extend my thanks once again to Steve for a really rich and informative presentation. and we'll look forward to the next one that we expect to be able to present to you guys in the next couple of months. So with that, I'll call the session to a close. Thank you.
Thank you, everyone.